Hi, this is Professor Fernandez. We're going to work on class notes E in lesson 17. The point of this class notes is to return to the system that we were studying in the previous video. And there we plotted four vectors in this direction field. And then we saw later in the video what the more general direction field looks like by using this website. So in this class notes, I want to explain that red curve at the end of it. That video, which I had mentioned, is what you get by following the arrows in the direction field. It traces out a curve. It looked like a circle, maybe an ellipse. We weren't sure. So in this video, we're going to explain what that circle or ellipse, thing looking thing is, and we are going to call it, as we did in this lesson, an orbit. So I want to run through quickly what you're going to see in the image that I'm about to switch to in that website, because I can't use a mouse on an iPad to show you that. So I'm just going to draw very quickly what that direction field looked like. There were arrows here that went northwest, arrows here that went west, and arrows here that went southwest, I should say, arrows here that went south. And then you just kind of got this picture of the direction field going in a counterclockwise circulation pattern. All right, so what we're going to see then is what I'm going to do is at the point 1, 0, I'm going to tap that point. And what the computer is then going to do is that it's going to take this system, which in matrix form looks like x dot equals negative yx. Oops, negative yx. So it's going to take this system with this initial condition, x of 0 equals 1, 0, because we're going to start at this point 1, 0, and it's going to solve the system numerically. So what does that mean? So it's going to, remember, at this 1, 0 point, in the previous video, we had calculated that the direction field vector points up. So what the system will do is that it will start here. It will then move a little bit in the up direction, maybe to this point, and then recalculate the value of the vector that is in the direction field at this point. And then it'll move it in this direction, and then the system will move here. It's at a new point, recalculate the direction field vector, go like that. So then what you're going to get is from 1, 0, you'll get another point, and then another point, another point, another point, right? And I've kind of spaced them out, but obviously the computer will do this very, very finely, and then it'll try to connect these points to yield some curve. And that's the red curve that you're going to see. All right, so then let's see that in action. So I'm going to switch over here. So this is the system. I've put it up here, negative y, x dot equals negative y dot equals x. And then I've also changed the domain and range here for x and y. And I've put Runge-Kutta 4. I mentioned in the previous video that that's a more accurate numerical scheme. I'll show you in a minute what happens if you don't do that, if you leave it as Euler. And then here I'm about to tap on the point 1, 0, which is all the way on the right on the x-axis, and you'll see the curve that results. So there it is. It's not quite 1, 0 because that point is actually on the axis, but it's effectively 1, 0 for our purposes. And you can see this circle ellipse looking curve that has resulted. And it's exactly what we described earlier. The web page is starting at 1, 0 and then following the direction field vectors. And then as it moves to the new point, recalculates the direction field vector, moves in that new direction, recalculates, and so on. So this is what we call the orbit through the point 1, 0. Now I'm just going to tap somewhere else. I'm going to tap on the point x equals 0.5, y equals 0. Right? So there it is. That gives me another orbit. And then I'm going to tap on the point x equals 0.25, y equals 0. That gives me that orbit. And then I'm just going to tap a bunch of times, right? So you can see that with this website, we can plot all these different orbits for the system. And obviously one thing you notice is that they all seem to be the same type of circles, ellipses. Again, we're not sure which one of these it is. And they seem to all be being traced out counterclockwise. So one of the things we'll talk about later on in the lesson notes, later on in the course, and later on in later videos is why, right? What about the system explains this circulatory pattern for its orbits? Why are they all circular? How come, some of them are not, I don't know, hyperbolic, and some of the other ones are circular? So we'll explain that. But I owe you this quick little discussion about what happens if you had kept Euler as your solution solver, as your numerical solver. So I'm going to go back and click on that 1, 0 point and have it calculate the orbit for me. And this is what happens, right? So there are all sorts of ways to approximate solutions to differential equations numerically. And excuse me, the Euler method is probably one of the fastest, but it's also usually one of the least accurate. And that's exactly what's happening here. So you shouldn't always believe what you see when you visit websites like this and try to have it calculate for you numerically what the direction field looks like, or any other function or graph. So that's one of the reasons I wanted to mention it. You know, if I start clicking around here, you see very, very different behavior. According to this numerical solver, you don't get closed curves. You get these spirals that spiral outward. When in fact, we will see later when we actually find the equation of the orbits for the system, that they will turn out to be circles, and we will prove that mathematically. So for our purposes, set the numerical solver, and you can see how the orbits change to what they should be, which is closed orbits, meaning the curve they trace out comes back to the same point eventually. So when you are, for our purposes, using this website to check your direction field work, make sure you've got that Runge-Kutta 4 setting on. Okay, so I'm going to go back to the lesson notes to just wrap up here. So I mentioned that little suggestion right below, and pretty much every time I send you or suggest that you go to this website, I will remind you that you should indeed set the numerical scheme to Runge-Kutta 4. So that's what I say down here. Okay, so that was a quick little run through of what an orbit is through a specific point for a system of first order ODEs.